In this lecture, I plan to develop the concept of a Lie derivative and then use Lie derivatives to define spacetime symmetries. So to begin, let me remind you of how we define covariant derivatives. We use the notion of parallel transport. So here's the idea. We have a curve. This is x mu parameterized by lambda. And we can define the tangent to this curve as the derivative operator d by d lambda. That's the tangent vector, with components t mu equals partial x mu with respect to lambda. Right, so now pick 2 points. Let's say this is point P, and here's a nearby point Q. And we have a vector field that's defined all along this curve. So here's, and we'll call the vector field V. So here's the vector V at point P. Here's the vector V at point Q. Let's also denote the change in the parameter lambda from P to Q as delta lambda. All right, so the idea behind the covariant derivative is that we transport this vector from point Q parallel to itself back to the point P. So using parallel transport as defined by the metric, we pull this vector from Q back to point P. So I denoted this as V sub Q with a little arrow to P. All right, and now we subtract these two vectors and divide by delta lambda to obtain the covariant derivative. So that's the limit of V at Q transported back to point P minus V at point P divided by delta lambda. And this is what I denoted using really not very standard notation as just dV d lambda. But we know now how to denote this. The muth component of this vector is T alpha del alpha V mu. That's the muth component of this dV d lambda. And by the way, I constructed this by taking the vector at Q and pulling it back to P and then subtracting, but we could just as well have taken the vector at P and pushed it forward along this curve to the point Q and then subtracted. So we could have just as well defined dV d lambda as the limit of V at point Q minus V at point P transported to point Q divided by delta lambda. It's really the same thing because remember we're taking the limit as the points P and Q coincide. So now let's look at the Lie derivative, which is based on the concept of Lie transport. So we start with the same construction. We have a world line parameterized by lambda. Let me go ahead and mark 2 points, point P and a point Q. And we have a vector field that's defined along this world line. So here's the vector at point P, and here's the vector at point Q. And let me remind you that the tangent to this curve is the vector T with components partial x mu with respect to lambda. Now in the case of the covariant derivative and parallel transport, we needed the metric to define the transport rule. For Lie transport, we don't need the metric, but we do need to have some more structure than what we have here. We need to assume that this vector field T is defined not only along this world line, but also in this entire region of space or space-time. So we need T defined everywhere, or at least in the neighborhood of this region. So in other words, let's say this is the vector T at point P, here's the vector T at point Q, here's the vector T at some later point along the world line, but we also have vectors T elsewhere. All right, now remember, whenever we have a vector field like this, we can define the integral curves of that vector field. In fact, this curve that we started with is one of those integral curves. But we can, given this vector field defined everywhere, we can draw integral curves through all these vectors. So the blue curves here are the integral curves of the vector field T, and they're just defined as the solutions of these differential equations, right? So this given T mu as a function of the x's, the points in space-time, this defines a set of differential equations, and we can integrate them. So for example, if we start with our initial conditions, say right here, and integrate forward in lambda, we find this curve. If our initial conditions have us starting here, then we integrating these equations, we have this curve, and so forth. So depending on the initial conditions, we get a different curve. And those are the integral curves of this vector field. So the idea of Lie transport is that we're going to take this vector v that sits at point P, and we're going to let it be swept along these flow lines of the vector field T until it reaches the point Q, and then we're going to compare or subtract that vector that's been swept along from point P to the vector that already sits at point Q. And we'll define then the Lie derivative, and I'll just temporarily call it dv d lambda, will be defined as the limit of v at point Q minus v at point P, but transported by the flow lines of the vector field T from point P to point Q, divided by delta lambda. By the way, I just realized I sometimes refer to these integral curves as flow lines, and that terminology comes from the analogy with fluid flow, where if this vector field were the velocity vector in a fluid, then these would be the flow lines of the fluid. So I'll also refer to these integral curves as flow lines. Let me try to make this notion of Lie transport a little more precise. So let me reproduce the figure. Here's the original world line, x mu parameterized by lambda, and the tangent is we're calling t. So the components of t are just the derivatives of x with respect to lambda. And we have a point P and a point Q. And now what I'd like to do is make use of the concept of a displacement vector that I introduced last time. So let me construct the displacement vector from P to Q. So here's the vector. And this is the vector delta lambda times t at point P. So in other words, this is the vector with components. The components are delta lambda t mu, which is from this equation writing partial x with respect to lambda as delta x over delta lambda. We see that the components of this vector are just delta x mu, where in this case, for this vector, delta x mu is the coordinates of point Q minus the coordinates of point P. That's the delta x here. All right, we have also a vector v here, and what I want to do is think of that vector also as the tangent to some curve. So let me draw the curve through point P. It doesn't matter what which curve I choose. Let's call that curve x mu of gamma. So this is a parameterized curve with parameter gamma, and it's defined such that the tangent to this at point P is the vector v at point P. And so I can create then a displacement vector from point P to some point, let's call it point R, which is the vector delta gamma times v at point P. And I can also do the same thing for the vector at point Q, the vector v. Okay, so I can draw a curve such that the tangent to that curve at point Q is v at point Q, and then I can make that into a displacement vector, which is delta gamma v at point Q. Now, if we go back to this point R, remember the vector field T is defined everywhere, so there are flow lines through every point in this region of the space or space-time. So in particular, I have a flow line that passes through this point R. Okay, and parameterized by lambda, I can then construct this displacement vector which is delta lambda times t at point R. Okay, so the idea now is we will transport this vector at point P by dragging its tail to the end of the green arrow here to point Q and dragging its tip to the end of the green arrow here. So that will give us a vector like this. And let's call that vector delta gamma times V at point P transported to point Q. Okay, that's this vector right here. So it's the Lie transport of this vector from P to Q. Okay, and now we subtract these two vectors, and the result is the Lie derivative. Okay, so in fact, if we go back up to this definition of Lie derivative, let me again write my temporary notation for the Lie derivative, dv d lambda, and let's multiply this by delta gamma. So what we have is the limit of delta gamma vq, so that's a displacement vector, this displacement vector right here, minus delta gamma times v p transported to q, that's this displacement vector, divided by delta lambda. Now let's remember that the components of a displacement vector are just the difference between the coordinates at the tip and the coordinates of the tail. So for this vector in particular, that's this vector, the components of this vector are just the coordinates here of the tip minus the coordinates of the tail. So let's write that out explicitly. We have delta gamma v p transported to q, and we're looking at the components of that vector. That's equal to the coordinates here. So what are the coordinates here? Well, we start with the coordinates at point P, and the coordinates here at point R are just obtained by adding the change in the coordinates, which is the components of this displacement vector, delta gamma vp mu. And then we also add the change in coordinates defined by this displacement vector, delta lambda tr mu. So there's the coordinates of this point, the tip of this displacement vector. The coordinates of the base are, well, starting from point P, we then add delta lambda times Tp mu. Okay, so we see here that, of course, these cancel, and we have delta gamma Vp mu plus delta lambda Tr mu minus delta lambda Tp mu. Okay, so now if we go back to this expression and we look at the muth component here, this is the vector delta gamma dv d lambda, the muth component. That's equal to the limit of 1 over delta lambda times delta gamma vq minus this result, delta gamma vp mu plus delta lambda tr mu minus delta lambda Tp mu. Now let's take a closer look at the components of the vector v at point Q. I see I forgot to put in the index here. So let's take a closer look at this term. we have the components of V at point Q. So the components of V depend on the point in space or space-time. So we're looking at the components at the point with coordinates x sub q. Let me go ahead and give it an index, say alpha. So if we remind ourselves of what the point Q is, in our diagram, it's this point right here. So it's displaced from the point P by the components of delta lambda times t. So this is x at point P plus delta lambda times t at point P. Right now, expanding this in a Taylor series, we have x at point P plus delta lambda t at point P alpha partial alpha v mu. This would be evaluated at point P. And then there are higher order terms that will drop because we'll be taking the limit as delta lambda goes to 0. Now we can do the same kind of calculation for this vector components. We have t mu at point R, that's t mu at the point with coordinates x sub r. And if we remind ourselves where that point is from the diagram, it's this point here that's displaced from point P by the components of this vector, delta gamma v sub p. So this is x sub p plus delta gamma v sub p. So now expanding that in a Taylor series, we have t at the point P plus delta gamma v sub p alpha partial alpha t sub mu, where again this is evaluated at point P, and the higher order terms were dropping. So now let's put these results together. First let's look at these two terms. We have delta gamma vq, that's all of this, and this of course is just the components of the vector v at point P. So you see this term times the delta gamma cancels this term right here. And all we're left with from these two terms is delta gamma times this term. And likewise, if we look at these two terms, delta lambda times t sub r at mu, we have this is t at point P times delta lambda, it cancels this term, and what we're left with is just this term here. So the result in the square brackets here will be this term times delta gamma minus this term times delta lambda. So let's write that out. We have delta gamma times dv d lambda, the muth component, is the limit of 1 over delta lambda times delta gamma times this term, that's delta gamma delta lambda tp alpha partial alpha v mu minus this term times delta lambda. Delta lambda delta gamma vp alpha partial alpha t mu. Okay, the delta lambdas cancel, and also we have delta gammas cancel. So what we're left with is the expression for the Lie derivative. The muth component is t alpha partial alpha v mu minus v alpha partial alpha t mu. And I've left off the subscripts p here because we're evaluating this in the limit where the points p and q coincide. So this is the Lie derivative of the vector field v with respect to the vector field t. The Lie derivative of v with respect to t. And it's denoted by a curly script L sub t v, and the muth component is what we've displayed here. So the muth component of the Lie derivative of v with respect to t is t alpha partial alpha v mu minus v alpha partial alpha t mu. We can extend the action of the Lie derivative to tensors of other rank. So let's start with a rank 0, 0 tensor, otherwise known as a scalar, or simply a function. So if f is a function, we define the Lie derivative of the function. Really the only option we have, it's the directional derivative along the integral curves of the vector field t. So this is the definition of the Lie derivative for a scalar function. Next, let's consider a type 0, 1 tensor, which is of course a covector. Let's let W be the covector, so it has components W mu. And to determine how the Lie derivative acts on W, we simply first let W act on a vector to form a scalar. And of course, in terms of components, that's W mu V mu. And this scalar function, we know how the Lie derivative acts on that. So we have the Lie derivative acting on W mu V mu. It's just a scalar, so it acts as a directional derivative. Now, we also insist that the Lie derivative satisfies the product rule, so this would be the Lie derivative of W acting on V plus W acting on the Lie derivative of V. And now we know how the Lie derivative acts on a vector, so let's write that. This is Lie derivative of W times V plus W acting on this Lie derivative, that's T alpha partial alpha V mu minus V alpha partial alpha T mu. Now let's compare this result to what we have from right here. Okay, if I expand this using the product rule, this is T alpha partial alpha W mu V mu plus W mu T alpha partial alpha V mu. And setting these two equal to one another, we see that this term cancels this term. And then what we're left with is Lie derivative of W times V equals, first this term, T alpha partial alpha W mu V mu. And then bringing this term to the right-hand side, we have W mu V alpha partial alpha T mu. And now notice we have a common factor of V in each of these terms. And I'd like to argue that we can cancel them because V is arbitrary. But first of all, I need to change this index to a mu to agree with the indices on V here and here. So let's change this index to a mu. And then we better change this index. We'll just go ahead and change that to an alpha. Right, and now we can cancel the V mu's across this expression. And what we're left with is the Lie derivative of W is equal to T alpha partial alpha W plus, from here we have W alpha partial mu T alpha. So this is how the Lie derivative acts on a covector. And now we can carry out this same type of analysis for a covector of any rank, say rank nm. So we have a tensor with n upper indices, mu1 through mu n, and m lower indices, nu1 through nu m. These are the components of the tensor. We just wire these together with vectors and covectors to form a scalar, and we know how the Lie derivative acts on that. We know how it acts on each of the vectors and covectors. So the only thing left undetermined is how the Lie derivative acts on the tensor. And the result is the Lie derivative along some vector field t of the tensor capital T, and we're going to look at the mu1 through mu n, nu1 through nu m component of that tensor. That's equal to T alpha partial alpha of capital T, mu1 through mu n, nu1 through nu m. And now for each of the upper indices, we have a minus sign, then t, first of all, for this index, let's replace it with alpha. Then we continue with the other indices, mu2 through mu n, and leave the lower indices alone. Then we have partial alpha t mu1. All right, and we'll do the same thing for mu2, mu up through mu n. So dot, dot, dot here represents n of these types of terms, one for each of these upper indices. And for each of the lower indices, we have t, leave the upper indices alone. And then for the first lower index, let's call it alpha. Then we continue with the other indices, leaving them alone. And we have partial, replace the index that we replaced here goes here, then t alpha. And we have similar terms for each of the lower indices. So this is the pattern for the Lie derivative of type NM tensor. As an example, let's write down the Lie derivative of the metric. So the mu nth component of the Lie derivative of the metric is t alpha partial alpha g mu nu, that's this term, and then we have two of these terms, one for each of the lower indices. So we have plus g alpha nu partial mu t alpha plus g mu alpha partial nu t alpha. Now let's turn our attention to spacetime symmetries. So let's start with the metric g mu nu dx mu dx nu, and I want to think of this as a line element, so it gives us the proper distances and proper times separating nearby points. So here's one point, and let's give this point the coordinates x mu. Here's a nearby point, and this point has coordinates x mu plus dx mu. So in other words, this coordinate distance, this coordinate separation is dx mu, and the line element tells us the proper separation between those points. And we have other nearby points as well. Here's one, here's another, all with their proper separations given by the line element. And now I want to consider a vector field T with flow lines that I'm drawing here. So these are the integral curves of some vector field. The x mu of lambdas of a vector field T. All right, and now let's let each of these points flow along the vector field. So for example, this central point will move up to here. So this is the point with coordinates x mu plus delta lambda t mu. So what I've done is I've displaced this point by this displacement vector, delta lambda t mu. So delta lambda t mu is a vector that points from this event to this event. All right, and similarly, we let each of these other points flow along these integral curves. So this point goes to here, this point goes to here, this point to here, and so forth. So now we look at this network of separations. This separation is d of x mu plus delta lambda t mu. So what do we mean by spacetime symmetries? Well, a spacetime is symmetric under the action of a vector field T if the network of distances is unchanged when we flow along the integral curves of T. So in other words, this network of distances is the same as this network of distances. So spacetime is symmetric if the network of distances is unchanged when the points flow along the integral curves of some vector field T. So that just means that this proper distance between these 2 points is the same as the proper distance between these 2 points. Now the proper distance between these 2 points is, well, the square of the proper distance is g mu nu at point x, let's call that x alpha, times dx mu times dx nu. The square of the proper distance between these 2 points is g mu nu at the point x, let's give it the index alpha, plus delta lambda t alpha times dx mu plus delta lambda t mu times dx nu plus delta lambda t nu. So that's the proper distance between these 2 points. So if we set those equal to one another, we have g mu nu at point x dx mu dx nu equals g mu nu at point x plus delta lambda t times dx mu plus delta lambda t mu times dx nu plus delta lambda t nu. And now we'll expand each of these 3 factors in a Taylor series. So this is g mu nu at point x plus delta lambda times t alpha partial alpha g mu nu plus higher order terms that I won't write since we're taking the limit as delta lambda goes to 0. The next factor is dx mu plus delta lambda times partial alpha t mu dx alpha. And the final term is dx nu plus delta lambda partial alpha t nu dx alpha. And by the way, I've used repeated index alpha here and again here and again here. I probably should have used different letters here and here, but the context usually makes it clear. There's a sum over alpha here, another sum over alpha here, and a sum over alpha here as well. All right, if we expand this out, we have a term that, well, first of all, we have this term, the term that's independent of delta lambda. And that, of course, is just this term right here, so those will cancel on the 2 sides of the equation. And then we have this term, delta lambda t alpha partial alpha g mu nu times these 2 factors, dx mu dx nu. We have the term g mu nu of x times this factor, delta lambda partial alpha t mu dx alpha times this factor, dx nu. And finally, we have g mu nu at point x times dx mu times this factor, delta lambda partial alpha t nu dx alpha. So this simplifies to 0 equals these 3 terms, and I can cancel out the delta lambda in those terms. This is t alpha partial alpha g mu nu dx mu dx nu plus g mu nu times partial alpha t mu dx alpha dx nu plus this last term is g mu nu partial alpha t nu, then dx mu dx alpha. So we have a common factor of dx mu dx nu in each of these terms, but the indices are not lining up. So let's change this index to mu, and then we better change this index to something else like alpha. And likewise here, we want to change this index to nu, and so we should change this index to something else like alpha. So now we can cancel the dx mu dx nu in this equation, and what we have is 0 equals T alpha partial alpha G mu nu plus G alpha nu partial mu T alpha from this term, and the last term is G mu alpha partial nu T alpha. Of course, you should recognize the right-hand side. This is just the Lie derivative of the metric with respect to the vector field T. So what we found is the following result. Spacetime is symmetric along the integral curves of a vector field T if the Lie derivative of the metric with respect to T vanishes. And the vector field T that defines this symmetry is called a killing vector field. Before I continue, let me make a comment about notation. I've been using the letter T for the vector field. That choice comes from the first letter in the word tangent for tangent vector, but it's probably a bad choice because we often use the letter T for one of the coordinates. So let me change the T to something a little bit less used, like K for killing vector. So the condition that the spacetime has a symmetry along the integral curves of some vector field, which we'll usually call K, is that the Lie derivative of the metric with respect to K vanishes. Now I'd like to pose a question. What if one of the coordinate basis vectors is a killing vector field? Right, so here's my coordinate grid. So these are the, say, the x0 coordinates. Here's my x1 coordinates, and so forth. Now, what I really mean by these coordinate lines is, for example, this coordinate line, this is a line along which x0 is varying while keeping x1, x2, and x3 constant. So these curves are really the integral curves of d by dx0, what we've been calling one of the basis vectors. And likewise, these curves here are the integral curves of d by dx1. So what I'm asking is, what if one of these basis vector fields, like, for example, d by dx0, what if d by dx0 is a killing vector field? Well, let's take a look at what the condition for a killing vector field tells us. We have the Lie derivative along the killing vector field of the metric vanishes. So that's K alpha partial alpha G mu nu plus G alpha nu partial mu K alpha plus G mu alpha partial nu K alpha equals 0. And what are the components of this killing vector field? Well, the components are, this is a basis vector, so the components are simply 1, 0, 0, 0, right? If we expand this in a linear combination of basis vectors, it's already a basis vector, so those coefficients are 1, 0, 0, and 0. So putting this into our expression for the Lie derivative of the metric, of course, this term vanishes because the k alphas are all just constants, so derivatives vanish. Likewise, this term vanishes, and this is just the derivative with respect to x0. So what we have here is just this equation just tells us the derivative with respect to x0 of g mu nu vanishes. So what this is telling us is if the metric tensor components are independent of one of the coordinates, say x0 coordinate, then the basis vector field d by dx0 is a Killing vector field, and the space-time is symmetric. Under translations, along the x0 coordinate lines. Now we have to be careful in using this result. If, for example, if g mu nu, the metric components, are not independent of any of the coordinates, that does not imply that there are no symmetries. Okay, we can have a metric whose components depend on all of the coordinates, and there are still symmetries. It's just that the Killing vector fields don't line up with the integral curves of any of the coordinates. Let's look at an example. So consider the line element minus e to the x dt squared plus dx squared, right? The metric components are minus e to the x 0, 0, 1. So notice they're independent of the coordinate t. So we can conclude right away that d by dt is a Killing vector field. So let's call it k. And we can check, of course, that the Lie derivative along k of the metric vanishes. So what this is telling us is that the geometry described by this metric has a symmetry along the t coordinate lines, along the d by dt direction. So the geometry is symmetric. Along the d by dt direction. In fact, if we look at more closely, here's the coordinate grid. Here's what I'm calling the t direction, d by dt. Here's x. If we look at 2 points along here, any neighboring points along one of these t coordinate lines, it has x equal to a constant. So this part of the line element vanishes, and we see that ds squared is negative. So that's telling us that the separation between these neighboring points is time-like. So in this case, we would call this a, say, a time translation symmetry. All right, so now the question is, what if we were presented this metric or this geometry but in a different set of coordinates? So let's change coordinates from t and x to, let's say, let t be t bar and x be t bar times x bar. So our new coordinates are t bar and x bar. And from these definitions, we have dt is dt bar, dx is t bar dx bar plus x bar dt bar. And now the line element is minus e to the power x, x is t bar times x bar, times dt squared, that's dt bar squared, plus dx squared. Dx squared is t bar dx bar plus x bar dt bar quantity squared. So we can collect terms here. We have an x bar squared times dt bar squared, so this is x bar squared minus e to the t bar x bar times dt bar squared. We have some cross terms, 2t bar times x bar dt bar dx bar, and finally the square of this term, t bar squared dx bar squared. So the components of the metric in these barred coordinates, call that g bar, are x bar squared minus e to the t bar x bar, t bar x bar, t bar x bar, and t bar squared. So written in terms of these coordinates, the metric depends on all of the coordinates. All right, but that does not imply that there's no symmetry. In fact, we know that there's a symmetry for this geometry, and we can work it out. So the Killing vector field was d by dt, so we just need to rewrite this in terms of our new coordinates. This would be dt bar by dt, d by dt bar, plus partial x bar with respect to t, partial with respect to x bar. Let's remind ourselves the coordinate transformation was t equals t bar and x equals t bar x bar. So we can invert this. We have t bar is equal to t and x bar is equal to x divided by t bar, but t bar is t, so that's x over t. So now we can use these to compute these derivatives. We have k is equal to partial t bar with respect to t is just 1, so this is d by dt, plus partial x bar with respect to t is minus x over t squared, then d by dx bar. Now we really need to write these coefficients in terms of the new barred coordinates. So this is d by dt, and I'm sorry, this should be bar, minus, well, x over t is x bar, and we have one extra factor of t in the denominator, which is t bar. So this is the Killing vector field, written in terms of the barred coordinates, and it's a symmetry of the geometry. And we can show that by just computing the Lie derivative of this metric along this vector field and show that it is equal to 0. Let's go ahead and show some of that calculation, but I don't want to keep writing bars on everything, so let me just rewrite the metric and the Killing vector without the bars. So this is x squared minus e to the tx. The off-diagonal terms are xt and xt, and this term is t squared. And the Killing vector right here has components 1 and minus x over t. All right, so what we need to compute is the Lie derivative of g mu nu along the Killing vector field t. Well, let me remind you, this is k alpha partial alpha g mu nu plus g alpha nu partial mu k alpha plus g mu alpha partial nu k alpha. So we just need to examine this expression component by component. So let's first look at, say, the tt component. All right, so the Lie derivative along k of the metric, the tt component, is just inserting mu and nu both equal to t. In this expression we have k alpha partial alpha gtt plus g alpha t partial t k alpha plus g T alpha partial T K alpha. Now you'll notice these two terms are the same because G is symmetric under interchange of its two indices. So let me just cross this out and put a 2 in here. All right, so this is the T component of K is 1, so we have partial T, GTT, plus, now the X component is minus X over T. So let me change this to a minus sign. We have minus X over T times the partial X of GTT. So that's this term with the sum over alpha put in explicitly. And now we have plus 2 times, well, one of these terms is in the sum over alpha is GTT partial T KT, and the other term is GXT partial T KX. All right, now KT is just 1, so the derivative of 1 is 0, so that term goes away. And what we're left with is the time derivative of GTT. GTT is this coefficient here. That's x squared minus e to the tx minus x over t partial x of that same coefficient, x squared minus e to the tx power. And then we have this term plus 2 gtx is just t times x. And we have the time derivative of the x component of k, that was minus x over t. Now let's simplify this result. We have minus x e to the power tx minus x over t times 2x minus t e to the tx plus, we have a minus sign here. Let me go ahead and bring that out. We have minus 2tx times the derivative of x over t is minus x over t squared. All right, so this is minus x e to the tx. This term is minus 2x squared over t. We have a plus, the t's cancel, so this is x times e to the tx. And from here we have plus 2 x squared in the numerator and t in the denominator. So if I haven't made any mistakes, all these terms should cancel. So this term cancels this one, and this one cancels this one. So indeed, this is equal to 0. And of course, we can easily check that all of the other components of the Lie derivative of the metric vanish. So the spacetime in this example contains a time translation symmetry. But the key lesson here is that depending on the coordinates you use, a symmetry might be very easy to identify or it might be very difficult to identify. So for example, in our original coordinates, here's the metric, and the symmetry was really easy to identify. We see that the metric is independent of the coordinate t, so d by dt is the Killing vector field. But if we were given this geometry written in these coordinates, and that's all you knew, it would be very difficult to tell whether or not there's a symmetry. And in particular, it would be very difficult to discover that this vector field is actually a Killing vector field.